So as I promised, though, before we get into like the frequency analysis, I'm going to do one more example on the AC analysis. But this time I'm going to do it at like two different like frequencies. And we're going to see like how we can actually approach a problem like that, right? Then we're going to start like talking about like frequency responses and like filtering. Example. Let's just say I'm given a circuit that has a voltage source with value cosine 5t. It's followed by a resistor and a capacitor. Let's just say this value over here is 4. This value over here is 4 as well. The value of the capacitor is 1/12. It's followed by a current source. And this current source is 2 cosine 2t. And I have an inductor with value 2 Henry. Right? Well, let's just say the question is, what is voltage across this 4 resistance? Okay, the question is, what is VT? Well, one way to do this, we already talked about it. We can write down a differential equation. We can find basically the equation that's representing that VT. We know like we have like two sources, both of them are like sine wave. So we know the force function would be a sine wave. So our particular solution is also a sine wave. So we can solve for particular solution and the complementary solution, and we know the answer, right? But we said like doing that could be a little difficult because we were going to have to like solve a second order differential equation with a force function that's a cosine, right? We said, what if we went from time domain to the frequency domain and then try to solve for that VT? The answer was like, yeah, we can absolutely do that. All we need to do is to like replace all the elements that we have by their equivalent. And if you recall, the equivalent, like for example, that inductor over there is I omega L, right? Which tells us it's actually operating at some frequency omega. By looking at the circuit, I have two sources and they have like different frequencies. So if I want to translate this to the frequency domain, what frequency should I use? The answer is like, we don't know, right? We know if we have a circuit that operates at one frequency, it doesn't matter like how many sources we have, as long as it's at one frequency, I can go from time domain to the frequency domain, solve the circuit in frequency domain, treat all the elements as a resistor. So I basically have a resistive circuit. I can solve it in frequency domain. And since there is a unique relationship between time domain and frequency domain, I can come back to the time domain, right? But in this case, that's not true. I cannot do that. What I do know is that looking at this circuit is still a linear circuit. Since this circuit is linear, I have superposition. If I do superposition, what it means is that I'm going to find the contribution of each source separately, and then I'm going to add them up in time domain, right? But let's just see like what happens if I want to find, for example, the contribution of the voltage source. If I want to find the contribution of the voltage source, I'm going to have to keep the voltage source and get rid of the current source. As soon as I do that, I have a circuit that operates at one frequency, right? So I can easily go from time domain to the frequency domain, solve the circuit in frequency domain, go back to the time domain, and use the exact same frequency that the voltage source has. And I can repeat this for the current source. Despite the fact that current source and voltage source have like different frequencies, when I zero out one of them, I only have like one frequency. So I can convert it to frequency domain, solve it, and come back to time, right? So let's see how it works. So let's find the contribution of voltage source. So contribution of voltage source. How do we find contribution of voltage source? We keep the voltage source. We zero out the current source. Basically zero out all the sources that we have besides that voltage source. In this case, it's just the current source, right? What does it mean to zero out the current source here? It means it's open circuit. If it's open circuit, what it means is that this portion of the circuit is gone. So my circuit in time domain looks like this: 4 times cosine 5t. I have this 4. I have 1 over 12. I have this 4. And I have this 2 Henry inductor. Right? So this is my contribution of the voltage source. So let's call this voltage over here V1 of t. Right? Now, by looking at this circuit, I have a circuit that operates at exactly one frequency. So I know how to take it to the frequency domain. I keep that in mind, that the frequency that this circuit is operating at is 5. Right? So I can translate it to the frequency domain using that frequency. So I know omega is 5. So I'm going to go to the frequency domain. Again, going from time domain to the frequency domain, the topology of the circuit would not change. The only thing that changes is the value of like the elements that we have. So I still have my capacitor, I have my resistors, and I have my inductor. All I got to do is to replace all elements by the equivalent. What is the equivalent value of this voltage source? Well, that would be the phasor representation of it, which is 4 with angle 0. For this resistor over here, we know it doesn't change in frequency domain, so it remains 4. This also remains 4. If I have an inductor, I have to change value of inductor L to I omega L. So I have I times omega, which is 5, times L, which is 2, which is 10I. If I have a capacitor, I have to change the value of the capacitor to minus I over omega c, or 1 over I omega c, right? So I have minus I divided by omega, which is 5, times c, which is 1 over 12. So it's minus 12I divided by 5. Right? Now I'm dealing with a resistive circuit. All I want to do is to find this voltage here. If I find this voltage here in frequency domain, I can always go back to the time domain, and therefore I know this V1 of t. Right? How do we do this? Do you agree voltage across this capacitor is exactly the same as voltage across the source? So it's 4. So what it tells me is that voltage from this point to this point is also 4. Right? So if I combine these two elements, what circuit do I have? I have a voltage divider, right? And as soon as I find voltage across this combined element, what I'm claiming is that I know voltage across this 4. Why? Because they're in parallel, and therefore voltage across each of them should be the same as voltage across the equivalent. So let's find the equivalent. What is the equivalent element here? I have 2 resistors in parallel. How do I find the equivalent? I multiply the values, divide by the summation. So the equivalent here is 4 times 10I divided by 4 plus 10I, which is 40I divided by 4 plus 10. Right? Therefore, V1 is voltage across this, which means I have 40I divided by 4 plus 10I divided by the summation of these two. So it's 40I divided by 4 plus 10I plus 4 times the value of the source, which is 4. Right? So that's a voltage divider. Let's simplify it a little more. I can write this as 40I divided by 4 plus 10I. 40I, let's find a common denominator, which is 4 plus 10I. For the second term would be 16 plus 40I. And the whole thing multiplied by 4. Right? This and this cancel. So what I get is that V1 is 40I divided by 80I plus 16 times 4, which is 160I divided by 16 plus 80I. Right? I can write this as some real part A plus some imaginary number B. How do I do this? I multiply this by the complex conjugate of the denominator. Right? And I can find A and B. As soon as I have A and B, I know the magnitude and the phase of V1. Right? So the phase and magnitude can be calculated using this. V1 is a square root of A squared plus B squared. Theta 1 is tangent inverse of B over A. Right? So I know exactly what V1 of t is. Right? What is V1 of t? Given this, V1 of t is this magnitude. Cosine, what is the frequency here? It's 5. So it's 5t plus theta 1. Right? So this is V1 of t, which is the contribution of this voltage source in time domain. Right? We cannot leave this in frequency domain, like over here, and then add them up in the frequency domain, because they have like different frequencies. Right? So they're happening at 2 different frequencies. So we cannot just leave them there and just add them up. To be able to add them up, we have to go back to time and use the superposition in time. Right? I got to do exact same thing for the current source. So I got to find contribution of the current source. How do we find contribution of current source? How do we do this? Yeah. Contribution of current source. We're going to have to keep the current source and zero out the voltage source. What does it mean to zero out the voltage source? It means a short circuit. So my circuit would look like this. 1 over 12. I have 4. I have 4. That's cosine 2t. And then I have this 2 Henry. Do you agree that this capacitor is gone? Yes? It is. Why? Because it's in parallel with this wire. Right? So voltage across this capacitor is 0. So it's gone. Right? Now I know this, I can actually go to the frequency domain. What is the frequency I'm working at? This time it's 2. It's no longer 5. It's 2. Right? Now I can redraw the circuit in frequency domain. The value of the resistance would not change. This remains 4. This current source becomes 2 and 0. And this inductor over here becomes I times 2 times this omega, which is 2, which is 4. What I'm looking for here is this v2 of t. Therefore, I need to find this v2. Right? Do you agree I can combine this 4 and this 4? What is the relationship between these two? They're in parallel, right? So I can combine them. So I can combine these two by 4 in parallel with 4, which is a 2, right? So my circuit actually looks like this. I have this 4i, I have this 2, and then I have this current source with value 2 and 0. Right? Let's call this current I prime. Do you agree I can find I prime? How? That's a current divider, right? So I prime is 4i divided by 4i plus 2 times 2, which is 8i divided by 2 plus 4i. Let's divide everything by 2. We get 4i divided by 1 plus 2i. Right? Do you agree this I prime is current through this 2, which means it's current through both these 4s in parallel? So as soon as it hits this node over here, it has to split between this 4 and this 4. Right? But since these two values are exactly the same, what is this current I? It's half of I prime, because this 4 and this 4, they got exactly the same value. I know the input current to this node would be I prime, so it splits equally in half. So I is I prime divided by 2, which is 2i divided by 1 plus 2i. Right? What is V2 then? What is V2? Well, the value of the resistance is 4 times current through it. What is current through it? It's negative I. Right? Remember, V2, this is positive, this is negative. I is going this direction. So it's negative I. So it's negative 8i divided by 1 plus 2i. Right? Again, I can write this as some a prime plus ib prime. I just need to multiply the whole thing by the complex conjugate of the denominator. And as soon as I do that, I can compute V2, which is the square root of a prime squared plus b prime squared. I can find theta 2, which is tangent inverse of b prime over a prime. Right? Therefore, I know V2 of t. What is V2 of t? Well, it's the magnitude times cosine. What is the frequency I have this time? This is 2 times. This is 2 times t plus theta 2. What is V of t then? V of t is V1 of t plus V2 of t. Right? And this is due to basically the superposition. Right? So the whole idea here was, since we had two separate frequencies, we had to do superposition in time domain. Right? We could not do superposition in the frequency domain because they got different frequencies. So we cannot add them up in frequency domain. So we had to go back to time domain and then apply the superposition. Yes. Correct. Yes. Yes. Right? Is that clear how we're doing this? So again, all the rules that we had, they still hold. As soon as I go from time domain to the frequency domain, and I replace the values by their corresponding values. Right? So that's pretty good, right? So that gives us like this idea that let's just think of any circuits that we're dealing with as a system, right? So let's just say I have this circuit. Let's just say I have this circuit. Some input voltage, some resistance, and some capacitor C. And let's just say voltage across this capacitor is V out, right? All I care about is that as soon as I know what my input is, I want to know what the output is. And if I change this input, I got to be able to compute this V out, right? So I can think of like the whole circuit here as a system, right? Which I want to know what's the relationship between input and output, right? Because that's essentially like what it is. If I basically tell you like this V input is a sine wave or is a step function, you can find like this output, right? So you can think of like the whole circuit here as a system with input V in of t and the output V out of t, right? Let's call this system H of t, right? As soon as I have like this H of t, I am hoping to find a relationship between input and output. It turns out if the system is very well behaved, basically if it is linear and time invariant, there is a very nice relationship between this output and this input. I'm not going to get into the details of like linear time invariant systems because that's a topic for like 2 or 3, which is signals and systems. But whatever circuit that we're dealing with, they're linear and time invariant, right? We already know the definition of a linear, right? It's additive and homogeneous. Time invariance basically means if I change the input, from time t to like t minus some tau, the output must change from time t to t minus tau, right? That's not the case for a lot of DC systems. All the systems we're dealing with, they satisfy this property. So it turns out if system H of t is linear and time invariant, then the relationship between output and input is through something that's called convolution, which is defined as an integral, which is integral from minus infinity to infinity, Vn of tau, ht minus tau, d tau. And since convolution is commutative, I can basically rewrite this as ht convolved with Vn, and rewrite this as negative infinity to infinity of h of tau Vn t minus tau d tau. Right? So what it basically says is that as soon as I tell you what the input is, and you know what the system is, you can compute this integral, and you know exactly what the output is. Right? But computing this integral can be very difficult. Because think about it. If I want to compute this integral, what I need to do is that I have to look at h of t, which is my system, look at the inverse of it, because I have negative tau, shift it by t, and then sweep it over the input and find the area underneath that as I'm actually sweeping over it. It's quite difficult to do that, right? But since we've been talking about like frequency and all those things, what if we go from time domain to the frequency domain? What happens? It turns out if I go from time domain to the frequency domain, this convolution, which is this integral, becomes multiplication. So going from time domain to frequency domain, this relationship V out as a function of omega becomes Vn as a function of omega times h of omega, which is much, much easier. It's multiplication, right? We call this h of omega, which is the relationship between the output and input frequency response. This is called frequency response. So if I have any system, if I find the relationship between input and output, I can basically find the frequency response. In this particular example, my input was voltage and the output was voltage, but it doesn't have to be. The input can be current, the output can be current, the input can be current, the output could be voltage, could be anything. So let me quickly rewrite this h of omega. Remember, I know V out is Vn omega times h of omega. Therefore, I can find h of omega as the ratio of output to the input, obviously in the frequency domain, right? So this is frequency response. But as I said, any ratio between output and input is also a frequency response. Yes? Just h of omega is the frequency response. Yes. Right? So any ratio of output to input is called frequency response. Obviously, it is happening in frequency domain. Right? I wrote down one of them over here, but it doesn't have to be like voltage. So h of omega could be the ratio of V out to V in, or it could be V out to I in, or it could be I out to I in, or it could be I out to V in. Right? It could be anything. Right? Basically, like it could be any of these four. Right? As soon as I know the input, whatever it is, voltage, current, anything, and as soon as I know the output, I can find the ratio, and that basically gives me like the frequency response. Right? But there is a tiny issue here. If I have this function h of omega, I want to be able to plot it. I want to be able to see like what it looks like. Right? Can I plot this h of omega though? Remember what happens when we go from time domain to the frequency domain. Everything becomes simpler. The catch was everything becomes complex. right? So can I plot this complex function? Why not? Because remember, note that h of omega goes from complex number to complex numbers, right? And if you remember, we said like complex number, they're similar to r squared. So this function h goes from r squared to r squared. So what is this graph actually located in? It's happening in R4. Remember, if you have like a function y equals f of x, what you're plotting is the tuple x and f of x, which happens in R2. Right now, your input here is a tuple, and your output is also a tuple. So if we want to plot it, it's happening in R4, which we have no understanding of it. We cannot plot it. We cannot plot anything more than R3. So we cannot really plot this. Instead, what we can plot magnitude and the phase of this h, right? The magnitude is happening in R. Phase is also happening in R. So we can simply just plot it, right? So instead, we cannot plot h of omega. Instead, we plot magnitude of h of omega and the phase of h of omega. So this is the magnitude, and this is the phase. We can't do that because they both are happening in R. We can simply just plot it. Even plotting this is hard. So we're going to have to approximate these two graphs. And it's called Bode plot. We're going to talk about it like next week. We're going to learn how we can approximate the magnitude of h of omega and the phase of h omega. And we call that Bode plot. So we're going to learn about Bode plot later, right? But for now, let's just try to understand this h of omega. Let's just see like when we can actually use this. Why are we even like talking about this, right? So let's just say I have a system. I have some input x of t, and I have my output y of t, right? And let's just call this system h of t. If you're taking like signals and systems, this h of t is called impulse response, right? We're not really like going deep into that and why this is called like impulse response and all those things. But just so you know, this is called impulse response. So this h of t is called impulse response, right? We know if the system is like very well behaved, it's LTI system. I know y of t is x of t convolved with h of t. We said it's actually quite hard to do, so we can go to like the frequency domain. And we know y of omega would be x of omega times h of omega, right? And therefore we define h of omega, which was our frequency response, to be y of omega which is any output, divided by the input. And this is our frequency response. Right? Again, remember this frequency response is a complex number. We decided to use plot the magnitude and the phase. What is the magnitude of h of omega? Since h of omega is complex, what is magnitude of h of omega? It's basically the magnitude of y omega divided by x omega, which we know if we're dividing two complex numbers, the magnitude would be the magnitude of the top divided by magnitude of the bottom. So that's magnitude of y omega divided by the magnitude of x omega. What is the phase of h omega? We're again dividing two complex numbers. So it's the phase of the numerator minus phase of the denominator. So phase of h omega is phase of y omega minus phase of x omega. Right? The very, very first application of this frequency response is filtering. Right? A very simple filter that you have is just your ear. That basically filters out all very high noises. And that's why you don't go deaf. Another simple application is when you're actually like using your phone. There are a lot of like filters in there to just reduce the noise that you have. Right? And it's all about this frequency response. Right? So the application is just filters. Right? But what are filters? Well, as the name suggests, filters are circuits that can eliminate or keep a range of a frequency for us. Right? So let's quickly define it. Filters. They are circuits that keep or eliminate a range of frequencies. So far in this class, we only learned about like passive elements. We only learned about resistors, capacitors, and inductors. And given these passive elements, we're only able to build 4 kinds of filters. We're able to build low pass filter, high pass filter, band pass filter, and band stop filter. So let's define these. Given passive elements R, C, and L, we can only build 4 types of filters. Type 1 is a low pass filter. Which, as the name suggests, it keeps all the low frequencies and rejects all the high frequencies. Right? So it keeps low frequencies and rejects high frequencies. If I look at the magnitude of this h of omega, and plot it against omega, I want to have something that keeps all the low frequencies and rejects higher frequencies. So it has to keep all low frequencies to like some frequency omega c and reject all of them. The magnitude here is 1. I'll explain in a second why that should be 1. Right? But that's basically like what it looks like. It keeps all the low frequencies and rejects all the higher frequencies. Right? Type 2 is a high pass filter. Again, the name is very intuitive. What it basically means is that we're going to keep all the higher frequencies and we're going to reject lower frequencies. Right? So it keeps high frequency and rejects low frequencies. Which again, if you plot the magnitude of it against omega, it should keep all high frequencies and reject low frequencies. Right? This is basically the ideal representation of it. Right? We're going to see that we're not able to get like this sharp edge. There's no way in real world that you can get this sharp edge. Right? So to smooth it out. But ideally, this is what's happening. Right? The third type is a band pass filter. What it basically does, it keeps a range of frequencies and eliminates whatever that's outside that range. Again, the name is pretty self-explanatory, right? So it keeps some particular range of frequencies and discard outside that range. Again, pictorially, if I look at the magnitude of h of omega, I want to keep certain range between like omega c1 and omega c2 and eliminate the rest of them. Right? And the last type is a band stop filter, which what it does is that it basically eliminates a range of a frequency and keeps whatever that's outside that range. Right? So it stops a range of frequencies and passes the rest. And if you look at like pictorially, it basically looks like this. Omega c1, omega c2. Right? It basically stops the range between like omega c1 to omega c2. Right? One thing you should notice is that I only plotted the magnitudes and not the phase. Because as it turns out, for most applications that we have, we only care about the magnitude, not so much with the phase. There are a lot of applications that we care about, like phase, but in most applications that we're dealing with in this course, we only care about the magnitude. For instance, your ear only cares about the magnitude. It doesn't care about the phase. Right? So we're going to like only draw this magnitude over here. We're going to talk about phase as well, but what we care about is like this magnitude. Right? But let's have like some intuition about this. right? We just define them, but let's just have like an intuition about it. So intuition. Let's just assume we have like a low pass filter. Okay. So assume we have a low pass filter. Remember, I have some input x of t. I have my system, and I get this output y of t. My system in this case is a low pass filter, right? So to be able to analyze it, I go to the frequency domain. So I get this x of omega. I get my system, and I have this y of omega, right? We assume like our system is like a low pass filter, so we know it should look like this. Right? Right? What is my output? What is y of omega? Well, remember, y of omega is x of omega times h of omega. So when I'm multiplying two functions, how do I multiply? We always multiply them pointwise, right? So assuming this is x of omega, this is the magnitude of it, right? This is my h of omega. This is some omega c. So this is h of omega. Again, we're only talking magnitude, right? If I multiply these two out, what is happening? Remember, this number over here is 1. What is the value that I have at this point? That is 1 times the value of x of omega. All the way till this omega c, I'm multiplying 1 by this x of omega. So what is my output then? This is exactly x of omega, because I'm multiplying 1 by this x of omega. What happens after x omega c? I am multiplying 0 by this x of omega, so I basically zero out whatever I have. So if I look at the output, up to this omega c, I have exactly the same as x of omega. But as soon as I hit omega c, this becomes 0. Right? And hence the name filter. What it does is that it basically keeps all the frequencies that are lower than this omega c and rejects all the frequencies that are greater than omega c. The same intuition holds for high pass filter. If I have like my x of omega, if I have a high pass filter, what I do is that I keep all the frequencies that are like higher than this omega c and zero out the rest. Same for band stop, same for a band pass filter, right? And hence, I have to have this magnitude here 1, because if it's like anything but 1, it basically stretches my x of t. So if this is, for example, 2, the output here is no longer x. The output would be 2 times of x. But what I want to just have as my output is exactly the x for that portion of the frequency. And that holds true for all other basically types of like filters that we're dealing with. Right? If you look at these, for the low pass filter and high pass filter, I only have like one frequency that I need to determine. So it turns out if I have a first order circuit, I can build these two circuits. But since I have two frequencies over here, I no longer can build this circuit using just one storage element. So I have to use like two storage elements. So these two circuits, basically if I have type 3 and type 4, these are second order filters or second order circuits. If I have type 1 and type 2, they're first order circuits. What we're going to be doing next lecture, we're going to actually start building these circuits. And we're going to see like how they actually behave. Any question? Yes. Yes. You're stretching your signal. All right, I'll see you guys Friday.